Okay, so I'm going to show you what I mean by the snowball problem. And essentially, what's happening is, so suppose, okay, suppose there is, by any for any reason, there is going to be a snowy incline, right? So this snowy incline is assumed to be infinite, right? So just suppose that the snowy incline is infinite. And now suppose that there is going to be a snowball, okay, a snowball of mass m. Okay. Now let's say that this snowball of mass m is initially a spherical snowball, right? It's a spherical. So initial shape is spherical. It's a spherical shape. Let's say that the initial speed is 0 meters per second. The acceleration due to gravity is negative 9.8 meters per second squared. And of course, let's just call this angle over here, let's just call the angle over here theta. It's just an arbitrary angle theta. Okay? Of course, theta cannot be 90 degrees. Okay, theta cannot be 90 degrees. That would just be free fall. I guess theta should reasonably be somewhere between, let's say that theta should reasonably be somewhere between 0 and 45 or maybe 60 degrees. Even 60 degrees is quite a lot. So let's say just between 0 and 45 degrees. And okay, so now we're going to assume that the distribution, well, I'm not going to make the assumptions. You make the assumptions. Okay, this is just like pretty much what I'm starting off with. And of course, it's going to have a moment of inertia. However, the friction over here is not entirely negligible, right? Of course it's snowy. It is snowy, yeah, but it's not negligible. So friction not negligible. And also don't forget that the friction is not just due by the pretty much the snow, the contact between the snow of the wall and the snow of the slope, but also the friction due to the air currents, right? Friction due to the air currents. Okay, so then you should probably consider that as well in your equations. There's going to be air currents, and so essentially the idea, right? The idea of what's going to happen is the snowball is going to start rolling down. It's going to start rolling down the incline, right? It's going to start to increase its kinetic energy, right? It's going to increase its kinetic energy, reducing its potential energy, right? Because the potential energy depends on the initial height. The initial height, h0, and then it starts to gain kinetic energy, translational kinetic energy, and rotational kinetic energy as it spins and spins a little more and more and more, faster and faster. Of course, along the way of the snowy incline, the snowball is going to start accumulating snow. So essentially, the idea is that the snowball will at some point accumulate such a large amount of snow, right? So essentially, it's going to start basically accumulating snow. And I leave it to you as an exercise to determine what kind of shape it will end up as. And so, at some point, like, realistically, how big, right? So some of the questions that we put out here is how big. So how big, in terms of, I guess, the radius and mass, will it get, right? So how big, right? How big will it get? And is there like a point where it just can't get any bigger and it just maybe collapses, right? Will it collapse at some point as it increases its mass? What's the density, right? What's going to be the distribution of the mass? Is the density going to be affected, right? These are all questions that need to be addressed for this problem. Of course, we're assuming no idealistic conditions, not at all, not at all. However, if you want to, propose mathematical model, to basically describe, so the mathematical model, whatever it is, I wanted to answer this question. I also wanted to determine the speed at any given time. I wanted to determine, the acceleration at any given time, and also the position at any given time. Those things are important to know. And of course, I want to know about the density rho at any given time. I want to know the density rho of the snowball. What else should we know about this? We should probably also think about, what's going to be the asymptotical behavior. So what's going to be asymptotical behavior? What's going to be the asymptotical behavior of this, this snowball rolling down the hill, accumulating more snow and more snow as it, touches more and more little pieces, little atoms of frozen water, of ice, right? It's more and more and more, and then we also want to talk about the moment of inertia, I, at any given time, right? This is all variable. It's all changing. It's changing. It's not it's not trivial, right? It's not a trivial problem. Okay, I guess you could also talk about the forces, some of the forces. Of course, logically there's going to be some air friction here, some drag. There's going to be some, friction due to the snow, although I would believe it might not be as much, right? Because, and I also want to know if at some instance, at some point in time, there's going to be slipping. So the question is, will there be slipping, right? Will there be slipping? Or if there isn't, what is the maximum normal force that, the normal force that this needs, what is it so that it starts to, it maybe collapses? These are all different questions that we can ask about this problem. Of course, if you change the angle theta, you're free to change the angle theta, and you can also think about what kinds of effects it will have on everything. So, yeah, this is the problem. It's not a trivial problem. That is true. It's a very non-trivial problem. And I have already looked at a couple of papers along the way, and they're pretty interesting. I have to say they're pretty interesting. They have pretty good proposals. I have read some of them. Some of them I don't understand, but I'll walk you through them, and I'll probably discuss them and see what my conclusions are. So we'll see what people come up with, and maybe you could answer it as well. You could try to answer it, of course, if it responds for you. Okay, so thanks for watching, and I'll see you next time.